So in this video, we'll calculate the concentrations of all the different conjugate acids and bases in a solution that is 0.20 molar potassium hydrogen sulfate. So one thing I want to tell you guys is that potassium K is a counter ion. It's K plus. What we're really worried about is the HSO4 minus. So don't be fooled about that K. It's K plus. This is an ionic solution, and it's an ionic solution composed of the ions K plus, potassium ion, and hydrogen sulfate, HSO4 minus. So we need to figure out the Ka for this. It's not part of our strong acid list, 6 strong acids. And looking at our table here, we have here HSO4 is, well, 1.3 times 10 to the minus 2. That's could be an issue with regards to our low ionization assumption. That is to say, it may ionize more than 5% because this is a pretty large number, compared to something like down the list 10 to the minus 11, 10 to the minus 8, 10 to the minus 19. 10 to the minus 2 is pretty large. So we need to write our equation and then figure out the concentration of all the different species that are in a bottle of 0.2 molar potassium hydrogen sulfate solution. That's concentration 0.2 molar in water. So here's our equation. Just as a reminder, acids do what acids do. They deliver protons. This water is going to take that proton, become a base. Water can be acid and base, weak acid and weak base. And then as a result, we will have our, so HSO4 minus gives off that proton, becomes sulfate ion. So that's the conjugate base partner. Water takes that proton and it becomes hydromonium ion. And this would be its corresponding conjugate acid. So they tell us in the problem that the concentration is 0.2 molar. Again, we're not concerning ourselves with the potassium plus 1 ion because it's just a spectator ion. So here we have minus x plus x plus x. So at equilibrium, this will be 0.2 minus x plus x and then plus x. I'm a little concerned about the magnitude of that Ka. It's significantly large that the low ionization assumption may fail. So the Ka here is going to be hydromonium ion, H plus. I use this and this interchangeably. SO4 minus 2, the sulfate ion, and all of that divided by HSO4 minus. The Ka given to us in this problem that we consulted from the table at, usually quoted at a specific temperature, 0.013 equals, so H plus is x at equilibrium. H plus is x at equilibrium. Sulfate is x at equilibrium. X plus x is x squared divided by 0.20 minus x. And I'm going to go ahead and assume x is small. So when we do that, this 0.013 Ka equals to x squared divided by 0.2. And then solving for x here, multiplying this by 0.2 and taking the square root will give us my value of x. And my value of x is also my value of the H3O plus and the value of the sulfate ion. So on my calculator, I'm getting a value of 0.051 big M. Here you want to put the units, which is our concentration of this and this. Let's check our assumption because again, that's a pretty high value. So let's check our assumption. We're going to take our x value, which is 0.051. We're going to divide it by the concentration of the bottle. The concentration in the bottle is 0.2. We will multiply it by 100. So this is our checking assumption, low ionization assumption. I'm getting 25% ionization. Okay, 25% ionization, which means we will have to do the quadratic rule for this. All right, so we won't have that on the exam, but I'll just go over this. This assumption is not valid. Sort of retreat, regroup, and then solve for x the old-fashioned way using the quadratic equation. So 0.013 times 0.20 minus x is equal to x squared. Okay, let's do the distributive property and like a train distribute this out. So 0.013 times 0.2, I can do that in my head. That's 0026 minus 0.013x equals x squared. So the quadratic equation is minus b plus or minus b squared minus 4ac, all of that over 2a. So we need to get into the right form. So it's going to be x squared, let's move it to the other side, plus 0.013x, and then moving it that side, minus 0.0026, all of that is equal to 0. Now it's in the right form to plug it into my quadratic equation. So minus b is minus 0.013 plus or minus the square root of b squared minus 4ac. So this square root b squared minus 4ac is called the quadrant. That's just a math term. So 0.013 squared minus 4a, a is 1c, okay, and that's actually a minus 0.0026. So putting a minus here converts that to a plus. And all of that divided by 2a, and a is 1. Let's do this on our calculator really quickly here. 0026 times 4 plus 0.000169. Okay, let's square root that thing. And that's 0.1008. So minus 0.013 minus a 0.1008 is a minus. You cannot have minus concentrations. So we will go with the plus version. So that's plus a minus 0.013. And divide it by 2. And I'm getting 0.0439. So I actually redid this calculation again on my calculator. It's actually 0.0449, so I apologize about that. And that's going to be our value of x. So what is x here? Okay, x is nothing more than our concentration of H3O plus as well as our concentration of sulfate ion. So the concentration at the end of the day of sulfate ion will be x. Here we had to use a quadratic because fortunately the ionization assumption didn't work. 0.0449. Concentration of H3O plus is going to be 0.0449. So it's same as. Concentration of hydrogen sulfate is going to be 0.20 minus 0.0449. And on my calculator, I'm getting 0.155. Okay, so don't forget to put in your units of molarity, moles per liter. So the big picture, if you have a 0.20 molar bottle of this, not just have hydrogen sulfate, you have protons and you have sulfate ion. All of this is in the solvent of water.